In this video, we're going to look at partial derivatives. And this is partial derivatives of multivariable functions. So let's take a step back and think about what derivatives were, or what derivatives told us in single variable functions. If I have a single variable function, I think of it as y is the output when x is the input in our function. And the derivative we could write as dy over dx, which is really giving me the change in y over the change in x. Notationally, we used f prime of x for the derivative. And what that told me was the slope of a tangent line. Remember, derivatives give slope of the tangent line. And slope of a tangent line essentially means how is y changing? How is my output changing as x is changing? So how is y changing as x is changing? And a lot of times we think of it that way. dy over dx, we think of it as the change in y over the change in x. The derivative is the instantaneous change, or the amount of change at that particular instant on the graph. Well, in two variable inputs, now we have two variables that can cause a change in our output. We're going to call our output z. So we could have a change in x causing a change in z, or we can have a change in y causing a change in z. And so we're going to get essentially two different derivatives. A derivative with respect to x changing, and a derivative with respect to y changing. And then later on, we'll see that we can actually change these at the same time, but at different rates, and see how that affects changes in z. But for right now, let's say changes in x are going to produce changes in z, and changes in y can produce changes in z. And that's the idea of the partial derivative. The partial derivative of f with respect to x is defined this way. Limit as h goes to 0 of f of x plus h comma y minus f of x comma y divided by h. Notice that what we're doing is we're keeping y the same, and we're letting x change by a very small amount. So this is telling me how much my output is changing as I'm changing my x. Now, notationally, we cannot use the prime notation anymore, because that would be ambiguous to our variable, which variable we're taking the partial derivative with respect to. So instead, we use this notation. F with a subscript x is the partial derivative of f with respect to x. We can do the same thing with y. Take the partial derivative of f with respect to y, There, that's better. With respect to y, is f sub y, which is the limit as h goes to 0. We're going to keep x the same, and we're going to let y change by a little bit, a very, very small amount. So this is the idea of derivative. If you go back to and look at the definition of derivative in a single variable function, it's exactly this, except we just don't have the comma y in this one, and we wouldn't have the x in this one. So it's the same concept. We just let x be our variable that we're changing. That becomes the partial derivative of f with respect to x. When we take the partial derivative of f with respect to y, we let the y value change. Now, notationally, I already said f sub x is the partial derivative with respect to x. F sub y is the partial derivative with respect to y. Okay, but you may see some other notations as well. You may see f sub x of xy. You may see this. This is delta over delta x of my function. That also symbolizes the partial derivative with respect to x. Sometimes you'll see d over dx instead of delta over delta x. You'll see delta f over delta x. That means the derivative of f with respect to x. And then since f is often written as f of xy equals z, you can just say delta z over delta x. That's derivative of z with respect to x, or just z sub x. So those are different notations, and all of these are called the partial derivative with respect to x, which is also known as the first partial derivative with respect to x. Basically, think first derivative. So we took a derivative with respect to x, we took a first derivative with respect to x. Now, how do we actually find these partial derivatives? Well, we've all taken derivatives before, at least I hope so at this point if you're watching this video. If we are trying to find f sub x, what we do is we treat x as a variable and we treat every y that we see as a constant number, just like any other number, whether it be a coefficient or a constant term or whatever. F sub x, we treat x as the variable and y as the constant. In a similar way, if we want to find f sub y, we treat y as the variable, and every time I see an x, I treat it just like any other constant number. So that's the key. If you can think that way, then finding partial derivatives is no more difficult than finding derivatives of single variable functions. In fact, that's what we're really doing. We're saying, let's pretend f is a single variable function in x. We treat the x as the variable, everything else is just a constant. And then we say, let's pretend that my function is a single variable function in y, treat y as the variable and everything else as a constant. Sometimes that takes a little bit of work to get used to, but once you get used to it, it goes fairly straightforward. Now, what does the partial derivative do in a multivariable function whose inputs are in R2? So let's assume this is a continuous function in R2. Well, f sub x gives the slope of the tangent line in the direction of x. So in a direction that's parallel essentially to the x-axis. F sub y is going to give the slope of the tangent line in a direction of y, meaning in the direction parallel to the y-axis. So these partial derivatives are giving tangent line slopes in specific directions. Let's take a look at an example. Let's take the function f of xy is equal to x squared minus 2x plus y squared minus 3. And we'll find the partial derivatives, which are also again called the first partial derivatives, f sub x and f sub y. And we'll evaluate those derivatives at the points 1, 0, and 3, 0. So let's start by taking the derivative with respect to x. We'll find f sub x. Now, you can also, again, write f sub x at any point x comma y, or you can just write f sub x for short. But we're going to take a derivative of this, viewing every single term where x is our variable and everything else is just constant numbers. So x squared, if I take the normal derivative of x squared with respect to x, I get 2x to the first. Remember, exponent comes down and then gets lowered by 1. Minus 2x gives me a derivative of minus 2. And then y squared, because there's no x in this term, y squared is treated just like a constant, like 18 or 24 or whatever. And we know that the derivative of any constant is 0. So the derivative of y squared is 0, just like the derivative of negative 3 is going to be 0. It's a constant term as well. So f sub x is 2x minus 2. F sub y, well, this time we're viewing the y's as our variable. So x squared is a constant term with respect to y. There's no y involved in that term. So that's treated just like any other constant, like 9 or 10 or 11, whatever. Derivative of a constant number is 0. Same thing with minus 2x. There's no y involved in this term. So derivative of that term is 0. Derivative of y squared is going to be 2y as long as y is my variable. And then derivative of 3 is 0. So those are my two derivatives. F sub x is equal to 2x minus 2. F sub y is equal to 2y. Now, I want you to notice this. Let's plug in 1, 0 into my function. 1 in for x, 0 in for y. 1 squared minus 2 times 1 plus 0 squared minus 3 becomes a negative 4. That equation tells me that when you plug in 1, 0, you get out a negative 4. But graphically, we're at the three-dimensional point 1, 0, 4. 1 is your x value, 0 is your y value, negative 4 is your z value. F sub x at 1, 0, that is what I get when I plug in 1, 0 into here. 2 times 1 minus 2. I guess I can write that down. 2 times 1 minus 2 is 0. So when I plug in 1, 0 into my f sub x, I get 0. If I plug in 1, 0 in my f sub y, well, f sub y is 2 times y. 2 times the y value is 2 times 0, which is 0. So at the point 1, 0, my f sub x is 0. My f sub y is 0. That means the slope of the tangent line is 0 in the x direction at that point, and the slope of the tangent line is 0 in the y direction at that point. We'll view that in a second. Now, let's say what would happen if I plugged in 3, 0 into my function? Well, I'd get 3 squared minus 2 times 3 plus 0 squared minus 3. I end up with 0. F sub x at the point 3, 0, excuse me, would be 2 times 3 minus 2. That's 6 minus 2. That's a 4. That means the slope of the tangent line would be 4 in the x direction. F sub y at that point, well, would give you 2 times your y value. My y value is 0, so I get 0. That means the slope of the tangent line in the y direction is 0. Let's take a look at what this means graphically. This function is going to give us a surface, and this f sub x and f sub y give us tangent lines or slopes of tangent lines at those given points. All right, so what I've done is I've graphed the surface. And when x is 1 and y is 0, z is negative 4. So we're at this point here, the point 1, 0, negative 4. If you look straight down, 1 in the x direction, 0 in the y direction, and then if you look from the side, you can see it's negative 4 in the z direction. So that's at the very bottom of this paraboloid. Now, if you think about the tangent lines, the f sub x is giving us the tangent line, the slope, in the direction of x. So if I'm looking at the cross section where I just see like the xz plane at that point, the tangent line is going to shoot out at slope 0 in the x direction. So again, I can make this as long as I want, but you can see that the tangent line is shooting out at slope 0 in the x direction. Now, if you look really close, in this case, it is exactly parallel. Well, it is parallel to the x-axis. In fact, in this case, it's in line with the x-axis too via the z-axis. So parallel to the x-axis. So that's what that f sub x equals 0. It means the slope of the tangent line in the x direction is 0. Now, what about the y direction? Well, the y direction is going to be the slope of the tangent line in the y direction. Notice that this is the tangent line in the y direction to my surface. And so at this specific point, we get, again, this parabola shape. And at the bottom of the parabola, we know the tangent line is 0. Now in this one, you'll notice when I said in the y direction, that doesn't necessarily mean it's on the z-axis or anything. What it is, it's parallel to the y-axis. So parallel to the y-axis. There. Going parallel to the y-axis. Hopefully you can see that and envision that. Now, as far as our other point was 3, 0, 0. And in that case, we got something a little bit different. We ended up with slope in the x direction. Again, we're at 3, 0, 0. So the way you do this is you do 3 plus some t value, 0, and then 0 plus the slope in the x direction, which would be 4. Okay. And then if you did the y, you'd start at 3, 0, 0. And you'd say, well, every time I increase t by 1 in the y component, since f sub y was 0, I'd go 0t in the z component. So hopefully that makes sense. Let me write that again. Slope in the x direction being 1 means every time I increase the x value by a unit, I increase the corresponding z value by 4 units. With the y, f sub y being 0, it meant every time I increase the y by a unit, I increase the z value by 0 units. So let's examine f sub x first. F sub x is 4. That means the slope of this line, when you look at the cross section of the xz plane, you end up with this line of slope 4. So as every time you move in the x direction, and we are moving in the x direction exactly, we're moving exactly along that x line. As you move parallel to the x, your z value is increasing by 4. So over 1 up 4. In terms of movement in the y direction, if you're on this curve and you move to the right, well, you're not moving up at all. You're just moving basically in a circular motion around the curve. So the tangent line in the y direction is going to be, again, parallel to the y-axis, but it's also going to be in the xy plane. So tangent line in the x direction is going towards x. It's saying as you increase x, how far up are you going? This says as you increase y, how far up are you going? Well, as you increase y, you stay around the middle. You stay around that circle. As you increase x, you're moving up the elliptic paraboloid. So that's the idea of these tangent lines and what the partial derivatives are actually giving you. Let's do another example with partial derivatives. Let's find the first partial derivatives, f sub x and f sub y, of this function. And then we'll evaluate those partial derivatives at the point 1, 2. So at the input value of 1, 2. We're going to do so with the function 7x to the third plus 8xy to the third minus 7y to the fourth plus 10. Let's go ahead and do that. First, I almost always take f sub x first. So I take the partial derivative with respect to x. This first term, 7x to the third, 3 comes down, multiplies, gives you 21x squared. Now, in the second term, we have a mixing of x and y's. But remember, my y's here are going to be treated as a constant. So they're essentially acting just, this y to the third term is essentially acting just like the 8 is in this term, or just like the 7 did in this initial term. This y to the third is just a number that's being multiplied by 8x. If you wanted to rearrange it, you could think of 8y to the third times x, where 8y to the third is the entire coefficient of x. So if I take a derivative of that, I'm going to get 8y to the third times 1. Minus 7y to the fourth, that's constant if we're taking a derivative with respect to x. So I get 0 when I take the derivative of that term, and I get 0 when I take the derivative of 10. So f sub x is that, 21x squared plus 8y to the third. And now I can go on and calculate my f sub y. By the way, once you get used to this, generally speaking, I don't rearrange the variables. I don't rearrange the order, generally speaking. All right, so let's take f sub y. Well, 7x to the third is a constant, so derivative of that is 0. 8x y to the third. 8x times y to the third. Y is my variable, so 8x is being treated as essentially a coefficient of y to the third. So the 3 is going to come down. 8 times 3 is 24. And I'm going to get 24x as the coefficient times y squared. That's kind of just like this term. 4 comes down, multiplies by -7, and I get -28 y to the third. So that x basically gets just treated like another coefficient. And then the derivative of 10 is just 0. Now, before I find the partial derivatives at the point 1, 2, I want to just state that when you plug in 1, 2 into the function, we get 7 times 1 to the third plus 8 times 1 times 2 to the third minus 7 times 2 to the fourth plus 10. And that all gets you a -31 when it's all said and done. Now my f sub x at the point 1, 2, well, I would plug in 1 in for x and 2 in for y. So we get 21 times 1 squared plus 8 times 2 to the third. So my f sub x becomes 85 when we're at the point 1, 2. My f sub y at the point 1, 2 becomes 24 times 1 times 2 squared minus 28 times 2 to the third. Whoops. So 24 times 1 times 2 squared minus 28 times 2 to the third becomes a negative 128. Let's take a look at what that does graphically and what that means graphically. Now, this one's going to be really hard to see because of the nature of the graph. It's very, very hard to graph, and it's a lot of really steep lines. But there's a point on this graph. That point is 1, 2, negative 31. And it's saying if we change x by a unit, then the z value should change by 85 of those units. And so we get a tangent line. And again, it might be hard to see this green line, but it's moving in the direction of x with slope 85. Can't see it because the surface kind of wraps around. And it's really hard to see that it's moving in the direction of x because it's such a steep line. But we get a very, very steep line, slope 85 there. And f sub y tells me if I increase y by a unit, then the z value will decrease by 128 of those same units. Again, hard to see, but if you're looking in the direction of y from here, we're getting a slope of negative 128. So almost straight down or very close to. And so as you move in the direction of y, slope of this blue line is negative 128. Again, this one's a lot harder to see, even though conceptually we may understand what's going on. Let's do one more example. Let's take f of xy equals 7 sine y divided by x. So let's take the first partial derivatives, f sub x and f sub y, and then we'll find the values when you plug in the point 3 comma pi. Now, the first thing to do before I take the partial derivatives is, because I have an x in the denominator, I will probably want to rewrite this as 7 times sine of y multiplied times x to the negative 1 power. I do that so that it's easier to take derivatives with respect to x and also with respect to y too, but with respect to x in particular. So if I take a derivative exponent of -1 will come down and multiply. Again, remember 7 times sine of y is just a constant number. So -1 times that constant number becomes -7 times the sine of y. And then I'd have to multiply times x to the -2 power. When I decrease my power by 1, I get a power of -2. Lots of different ways you can rewrite that. I'll rewrite it as -7 times sine of y divided by x squared. That'll make maybe my calculations a bit easier. If I take the f sub y, if I take the derivative with respect to y, this x to the -1 doesn't matter if I put it in the back or in the front, it works just like a coefficient. And so I need to be able to take the derivative of sine y times a constant number. Well, constants out front aren't going to do much. They're just going to stay in place. So derivative of sine is cosine of y. So I'm going to get 7 times the cosine of y times x to the -1 still. Or if I wanted to put that as a fraction, that's 7 times the cosine of y divided by x to the first power. So what's the partial derivative? F sub x. When I plug in the 0.3 pi, well, I'd have to take this output -7 times sine of pi divided by 3 squared. Now, sine of pi is 0. So this whole thing turns into a 0. How about the derivative with respect to y? Well, the derivative with respect to y of 3 comma pi, or at 3 comma pi, would be 7 times the cosine of pi, all divided by 3. Now, cosine of pi is -1, so I get -7/3 as my answer. By the way, I didn't say this, but when you plug in 3 pi into that original function, sine of pi, like I said, is 0. So I didn't calculate this, but f of 3 comma pi is also 0. So we're at the point 3 pi 0, and it's telling me my partial derivative with respect to x is 0, and my partial derivative with respect to y is -7/3. So let's take a look at this. We're at 3 pi 0. So 3 in the x direction, pi in the y direction, and 0 in the z direction. We're at this point here, if you can see it. So that point there. We get a weird surface, obviously. It does a lot of undulations and things like that. And what we're saying is, as far as the f sub x being 0, that means if I increase in the x direction by a unit, the z direction doesn't increase at all. So you see that the tangent line parallel to the x-axis is just flat along our plane, on our xy plane here. So we get a flat tangent line if you move parallel to the x-axis. So moving parallel to the x-axis is right here, you end up with that tangent. Now, if you're moving in the y direction by a unit, then the z direction is going to increase, or decrease, I should say, by 7/3 of a unit. Let's change the color on that. Actually, let me go from -4 to +4. Good. So it's hard to see when you look straight on because this is such a complicated surface, but you can see that as you move in the y direction, you're moving down in the z direction by 7/3 every time you move over in the y direction by a unit. So you go up a unit in the y direction, down 7/3 in the z direction. So that's the slope of the line. And you can see that it is tangent if you kind of zoom in a little bit into that spot. Again, maybe it's easier to see this way, but at that point, we get this tangent line. Okay. So in the x direction, we're not increase. If I change x at all, I basically stay at the same z level. But if you change y, you change your z levels. You're increasing. So hopefully that makes sense about what f sub x and f sub y are doing and how they're being measured and what they are measuring. Now let's take a second derivative. And when we take a second derivative, we're going to take a second partial derivative. So we take a second derivative. We've done that before. Well, I hope you've done that before. If you're watching this video up to this point, I'm sure that in Calc 1 or Calc 2, you've taken second derivatives. Now we're going to take second derivatives, and we're going to take second partial derivatives. If I take the second partial derivative of f with respect to x, then again with respect to x, I'm taking f sub x x. Basically, I'm going to take a derivative with respect to x of my f sub x. So long story short, I take a derivative with respect to x, and then I take another derivative of that resulting function with respect to x. Notationally, it looks like the second derivative of f with respect to x both times. F sub x x. A similar definition holds for f sub y y. I take a derivative with respect to y, and then I take another derivative, a second derivative with respect to y. So we get the second derivative of f with respect to y squared. The dy squared means I took a derivative of y both times. And this is analogous to a derivative or second derivatives in single variable functions. Now, here's something that doesn't happen with single variable function. I can take a mixed second partial derivative. So I can take a second partial derivative where my first derivative I take with respect to x, and then my second derivative I take with respect to y. Notationally, you go f sub x, then y. When I do this, I take the derivative with respect to x first, then the resulting function I take a derivative of with respect to y. A similar definition will hold if you go in the reverse order. You go y first and then x. Again, derivative of y comes first, and then after that, I take a derivative of x. We're going to see a feature here of the f sub xy and the f sub yx, which hopefully makes it a little bit easier to deal with. We'll see that in a little bit, but f sub x, then y, f sub x, then y, you take a derivative of x first, and then derivative of y. F sub yx, you take a derivative of y first, and then a derivative of x. So let's go back and find all of the second partial derivatives of this function. This is a function we saw earlier. This was my example 1 function. F of x, y equals x squared minus 2x plus y squared minus y. Let's find all of the second partial derivatives. Now, when I say all of the second partial derivatives, there's going to be 4 of them. I can do xx, I can do yy, I can do x then y, or I can do y then x. So we'll find all of those second partial derivatives and figure out what they are at the point 1, 0. Now, obviously, I'm using the same function, so I can take advantage of the previous work. So we've already found the first partial derivatives. The first partial derivatives are just f sub x and f sub y. Now we want to find the second partial derivatives. So if I'm going to do f sub xx, I'm going to start by taking a first partial derivative. I've already done that. And then I take a derivative of that function with respect to x again. So derivative of this with respect to x is actually just a constant of 2. F sub yy, well, I'm going to take a derivative with respect to y. I've already done that. And then I'll take a derivative of that function. Derivative of that function with respect to y is just 2. Now let's do the mixed partials. Let's go f sub x y first. This is where I take a derivative with respect to x first. So I took a derivative with respect to x right there. And then I take a derivative of that resulting function with respect to y. Now in this case, I have 2x minus 2. When I take a derivative of that with respect to y, both of those are constants with respect to y. And so I get derivative is 0 minus 0, or 0. F sub yx, well, I take a derivative with respect to y. I've already done that. I got 2y. A derivative of 2y with respect to x is 0. So I'd get 0. Now, in this case, all of these are constants. So at the point 1, 0, let me copy and paste. So at the point 1, 0, f sub xx is 2. At the point 1, 0, f sub y is 2. At the point 1, 0, f sub xy is 0. At the point 1, 0, f sub yx is 0. They're all just constants. So here we found the point. We've found the first derivatives. And now we've found all of the second derivatives, all of the mixed partial second derivatives. Mixed and partial second derivatives. So we've found all of the second partial derivatives right here. Now, what do the second derivatives tell me? Well, they tell me something about concavity in the x direction when I do xx. They tell me something about concavity in the y direction when I do yy. And the mixed are a little bit harder to understand. There's something about, overpowering your first concavity. I won't get into that. Let's take a look at this example. This example was my example 2 from earlier. And we're going to do the same thing. We're going to find the second partial derivatives, f sub xx, f sub yy, f sub xy, f sub yx for this function. Again, this is a function that I've already taken my first partial derivatives, and so I can piggyback off of that to find my second partial derivatives. If I hadn't already found my first partial derivatives, then I need to do the first partial derivatives in order to get the second partial derivatives. All right, so again, we're piggybacking off the work we did earlier. We've done an f sub x and an f sub y from this function we had earlier. If you forget how to do that, just rewind the video and go check that out. So let's do f sub xx, the second partial derivative, both with respect to x. That means I would take this function, 21x squared plus 8y to the third, and take the derivative of that with respect to x. The first term, I'd take 2 times 21. That would give me 42 times x to the first. And then the second term of 8y to the third, with respect to x, that is a constant, and therefore it'll be 0. So f sub xx is 42x. Let's do f sub yy. Well, that means I would take this function and I would take the derivative of that with respect to y. Again, 24x is a constant, but it's in the place of a coefficient. So I'm going to treat it like a coefficient. 2 multiplies, and I get 48x times y to the first for the first term. And then in the second term, 3 times negative 28 is going to be negative 84. And then I'm going to get y squared. So f sub y is 48xy minus 84y squared. Let's do f sub xy. So I take the derivative with respect to x. I already did that. And now I take the derivative of this with respect to y. Now, with respect to y, the 21x squared is a constant, so that's going to become 0. And 8y to the third, the 3 comes out front, I get 24y squared when I take the derivative. So I get 0 plus 24y squared. Let's do f sub yx. This is where I take the derivative with respect to y. Again, we've already done that. And then I take the derivative of this function with respect to x. Now, with respect to x, this second term goes to 0 when I take the derivative because that's a constant with respect to x. This y squared I could put in front of the x like a coefficient. And because this is a constant in the place of where the coefficient would be, taking the derivative of a constant times x just gives you the constant times 1. So I get 24y squared. Again, once you get used to that, you don't have to move the x around to see it. So here are my 4 second partial derivatives: f sub xx, f sub yy, f sub xy, and f sub yx. Notice f sub xy and f sub yx happen to be the same function. That also happened with the previous. The mixed partial derivatives happen to both give you 0 in the previous case. Here, they get 24y squared. Now, if we're evaluating these things at the point 1, 2, all I do is plug in the point 1, 2 into each of these. So f sub xx at the point 1, 2 gives me a 42. F sub yy at the point 1, 2 gives me, I don't know what that's going to be, but we'll figure it out on my calculator. So I'd take 48 times 1 times 2 minus 84 times 2 squared. And I got negative 240. Hopefully my calculations are right. If they're not, I apologize for that. If I plug in 1, 2 into f sub xy, what I end up doing is replacing the y with the 2. And so you get 24 times 2 squared, which is 96. Same thing here if I plug in the point 1, 2. 24 times 2 squared becomes 96. And again, these might not seem like too much going on right now with these second partial derivatives. They're related to concavity and whether we get relative minimums and relative maximums and things like that. We'll see they're related to concavity, but not in a as direct of a way as you may hope. Okay, we'll see that in later videos, how these second partial derivatives can inform some ideas about what the point looks like, or how the surface is shaped at that specific point. But there you go. Well, since we did the other two functions that we've previously taken the first partial derivatives of, let's take this third function and let's find the second partial derivatives of this third function. And then we can find those second partial derivatives, what they're evaluated at when at the point 3 comma pi. Once again, there's no use of redoing work we've already done. We've already found the first partial derivatives. In fact, I can kind of, I'm going to use the negative exponent version of those. So let's find the second partial derivatives, f sub xx. I take my f sub x and I take a derivative of this with respect to x. The -2 would come out front. That would give me a positive 14 times sine of y times x to the -3rd. F sub y, why? Well, the derivative of cosine of y is going to be negative sine of y. So I'm going to end up with -7 times sine of y times x to the -1. That x to the -1 I could have brought up front and treated like a coefficient of the cosine function. I'm not going to do that. I'm not going to bring it up front every time. I'm just going to be able to see it, hopefully. Let's do f sub xy. So once again, I'm taking derivative with respect to x first, and then I'm taking that highlighted function, and I'm going to take a derivative of that with respect to y. The derivative of sine of y is cosine of y. This x to the -2, this -7, those are just like coefficients. So I'm going to end up with -7 times cosine of y times x to the -2. Then let's take f sub yx. That's where I take the derivative with respect to y first, and now take the derivative with respect to x. This 7 cosine y is treated just like a coefficient. So I take the -1 out front and reduce the exponent by 1. That's going to give me a -7 cosine of y times x to the -2 power. Again, notice what's going on. F sub xy and f sub yx became the same thing. That's happened in every example that we've done so far. And it turns out that's always going to happen. We'll explicitly state that on a slide in just a second. Now, if you want to plug in 3 pi, into all of those, we can just plug in 3 pi into each one, 3 pi into xx. Well, sine of pi, we've already established is 0. So you get 0 times 3 to the negative third power, you just get a 0. Whoops. If you plug in 3 pi into the f sub y, again, sine of pi, x becomes a 3. We get 0 times 3 to the negative 1. 3 to the negative 1 is not a problem, so you get 0. Plugging in 3 pi into the second mixed partial derivatives, the f sub xy and the f sub yx, we have to get the same thing. When you calculate this out, you actually get negative 7/9. 3 to the negative 2. I'm sorry, cosine of pi is negative. So negative of negative 7/9 is a positive 7/9. My mistake. So negative 7 times cosine of pi is going to give you a positive 7. And then 3 to the negative 2 is essentially dividing by 9, dividing by 3 squared. And you get the exact same thing when you do the yx. And you have to, because f sub xy and f sub yx gave us the same thing in this example, and in the previous example, and in the example before that. That is not a happenstance. That's actually on every function that's going to happen where the second partial derivatives exist. So obviously sometimes second partial derivatives, mixed partials may not exist, but if they do exist, if I can take the second partial derivative f sub xy, you'll get the same thing if you do f sub yx. So if you ever forget, well, should I have taken the derivative with respect to x first or with respect to y first? It really doesn't matter as long as you take one with respect to x, one with respect to y, you should end up in the same place. And by the way, the reason for that is that when you take a derivative with respect to x, you're changing the x component, the x value. And when you do that with respect to y, you're changing the y value. And with limit as x, limit as h goes to 0 in the x component, limit as a different h, let's call it h1, goes to 0 in the y component, you can interchange those limits and get the same thing. So because of the definition of derivative, this always has to happen. Okay. Now, let's do another example. This one we haven't done before. So let's take the first and second partial derivatives for this function. F of xy equals tangent of x times y to the fourth. We'll take the first and second partial derivatives. We don't need to plug anything in this instance. On this one, we're going to have to do a little bit more computation than we did in our first three. Because this is a tangent, I have to remember that the derivative of tangent is secant squared. Now I have an x inside the argument of tangent. So when I take the derivative with respect to x, I'm going to get secant squared of xy to the fourth. So secant squared of the argument. And then I'm going to multiply that by the derivative of the inside function. The derivative of the inside function with respect to x is going to be y to the fourth. It's like having a coefficient of y to the fourth times x to the first. So that's my f sub x. My f sub y, well, again, y is inside the argument of tangent. So derivative of tangent is secant squared of x, y to the fourth. Chain rule then says I have to multiply times the derivative of the inside function. The derivative of the inside function is 4x y to the third when I take the derivative with respect to y. So those are my two first partial derivatives. My second partial derivatives, let's do f sub xx first. Notice this y to the fourth is essentially just a coefficient of the secant squared. So when I take derivative with respect to x, first off, this y to the fourth is just going to be kind of like a coefficient. And then I'm going to look at this as secant squared. So it's a lot of chain rules, but basically I take 2 times secant of x, y to the fourth. So the exponent of 2 has to come out front. I lower the exponent by 1. And then I multiply. So this is all raised to the first power. Oh, no, I see what I'm doing. Okay, that's all raised to the first power. Then I have to take a derivative of secant x, y to the fourth. Derivative of secant is secant of the argument times tangent of the argument. And then I have to take a derivative of the inside piece. Again, that's with respect to x. So I get another multiplied by y to the fourth. Now, if you want to clean this up and rewrite this, you can make it look a little bit nicer. F sub xx, you'll notice that the y to the fourth and the y to the fourth can be multiplied and give you 2y to the eighth up front. We have here a secant x y to the fourth, another secant x y to the fourth. So I can take that secant squared of x y to the fourth. And then I still have the tangent of x y to the fourth. So f sub xx cleaned up looks like that. Notice that that's a pretty complicated thing to do. If I do f sub yy, well, it's going to be even more complicated because I have a product rule, and when I take the derivative of this, I have a chain rule. So it's going to be product rule mixed in with a chain rule, mixed in with a second chain rule. So I'd start, once again, 2 comes out front. So I'm going to call secant squared. This is going to be my first component. And then the 4xy to the third, that's going to be my second component. So the product rule says take the derivative of the first component times the normal second component plus the normal first component times the derivative of the second component. Now the derivative of this second component is going to be 3 times 4, that's 12xy squared. And so that part's good. That part's pretty easy. The derivative of this, I'm going to have to take 2 times secant to the first power of x, y to the fourth multiplied times the derivative of secant. Derivative of secant is secant times tangent multiplied times the derivative of the argument, which is 4xy to the third. And yeah, that's quite the hot mess. We'll clean it up just a little bit. F sub y is equal to, well, in this first part, I get 4xy to the third times 4xy to the third times 2. That's 32 x squared y to the 6. I have secant times tangent. So secant squared times tangent to the first. And then plus the other part, which was secant squared times 12xy squared. I'll put the 12xy squared up front, multiply that times secant squared of xy to the fourth. You can see what's happening, and what we're trying to show is that sometimes these things, especially in the second derivatives, can get pretty messy. Okay. Let's do f sub xy. Now, the nice thing about doing the mixed partials is now we know they should give us the same thing. So if I see one that's a little bit easier to do than the other, I might choose that one. Both of these are going to be kind of difficult. So I think what I'll do is I'll just take my f sub x right there, and I'll take the derivative of that with respect to y. I still have this product rule. So again, if I take my first component as secant squared, my second component as y to the fourth, product rule says I take the derivative of the first component times the normal second component plus the normal first component times the derivative of the second component. Derivative of the second component here with respect to y is 4y to the third. Again, I'm taking the derivative of this one with respect to y. Derivative of that first component with respect to y is going to be, well, 2 secant to the first power times the derivative of secant, which is secant times tangent, times the derivative of the inside function with respect to y. That would be 4xy to the third. That's what I get when I take that mixed partial. And again, I can clean this up if I want to. And I can say, moreover, since I know that derivative f sub x y is going to be the same thing as f sub yx, I don't have to do it again. I'm going to get, well, let's look through. I have 2 times 4 times x times y to the third times y to the fourth. That looks like it's going to be 8xy to the seventh multiplied times secant squared of xy to the fourth multiplied times tangent to the first of xy to the fourth. All of that. Then we're going to add secant squared of xy to the fourth times 4y to the third. I think I'll put the 4y to the third in front of the secant squared. Hopefully that looks a little bit nicer. Again, these are not easy functions to deal with. We needed to remember lots and lots of different derivative techniques. In particular, we needed to do sort of a chain rule inside of a chain rule in order to be able to take a derivative of secant squared x times y to the fourth. So we need to do a chain rule inside of a chain rule. And because we have two functions multiplied times each other, we also needed to be able to do a product rule in with that. So lots and lots of different rules, but now I have the 2 first derivatives and then all 4 second partial derivatives. And we started with just this function here. Again, notice how ugly that got that quickly got pretty ugly after second derivatives. Let's do another example. Let's take our function to be the square root of 8x to the third times y squared minus 9. That 8x to the third y squared minus 9 is all under the square root. And we'll try to find the first and second partial derivatives of this. There's going to be 2 different first derivatives and 4 second derivatives. Now, the first thing I'm going to do before I even take any derivatives is I'm going to rewrite this as 8x to the third y squared minus 9, all raised to the 1/2 power or the 0.5 power. It doesn't matter whether you call it the 1/2 power or the 0.5 power. The reason I do that is because when I take derivatives, I'm going to have to use the chain rule. And when I use the chain rule, it's a lot easier to use exponents rather than square roots. So I'm going to use the exponents 1/2. So if I take the derivative with respect to x, 1/2 is going to come out front. I'm going to multiply times that inside function. Now that inside function is not going to be raised to the 1/2 power, but to the negative 1/2 power, because that's 1/2 minus 1. And then I need to multiply times the derivative of the inside function. Now, with respect to x, the derivative of the inside function is 24x squared times y squared plus 0. If I wanted to, I can rewrite this and say this coefficient of 1/2 can multiply times 24x squared y squared and give me a 12x squared y squared. So the 1/2. I can't distribute the 1/2 inside here because of this exponent, but the 1/2 I can multiply times the derivative of my inside function. That makes things look a little bit nicer. Let's do the same thing for y. Well, again, y is inside, so I'm going to take the 1/2 out front times the normal function, 8x to the third y squared minus 9, the normal inside function, raised to the negative 1/2 power. Now the derivative of the inside function with respect to y is going to be, I'm going to take the squared, multiply it out front. I'm going to get 8 times 2, which is 16, x to the third times y to the first. Again, if I want to take and rewrite this, that 1/2 times 16 can turn into an 8. That makes my life a little bit easier. So those are my first partial derivatives. My second partial derivatives, I'm going to have to use, again, the product rule and chain rule and all that stuff. So I'm going to take derivative of the first component times my normal second component. My first component is going to be that mess. I'll take the derivative of that in just a moment, times my normal second component, 12x squared y squared, plus my normal first component, which is going to be 8x to the third y squared minus 9 raised to the negative 1/2 power. That's my normal first component, times the derivative of my second component, and this is the derivative with respect to x. So I'm going to get 2 times 12, that gives me 24, x to the first power, y to the second power. Now, what's the derivative of my first part with respect to x? The derivative of that with respect to x. The negative 1/2 is going to come out front. I'm going to get normal inside, the inside function, 8x to the third y squared minus 9. I'm going to lower the exponent by 1, so that exponent is going to go from negative 1/2 to negative 3/2. And then I have to multiply times the derivative of the inside function with respect to x. Once again, that's 24x squared y squared. I'll clean this up a little bit. Negative 1/2. Well, let me use another line. So I'm going to take negative 1/2 times 24x squared y squared times 12x squared y squared. That gives me negative 144 times x to the 4th times y to the 4th. All of that is going to be multiplied times 8x to the 3rd y squared minus 9 raised to the negative 3/2 power, or the negative 1.5 power. And then the second one, I'm just going to write, I'll write 24xy squared times 8x to the 3rd y squared minus 9, all raised to the negative 1/2 power. So that's my f sub xx. My f sub yy, I take the derivative of this with respect to y. And again, it's going to be the derivative of that first component times my normal second component, 8x to the 3rd y, plus the normal first component, unchanged, times the derivative of the second component. Now, the second component, derivative with respect to y, is going to be 8x to the 3rd, because that's just a y to the 1st. So we're going to get 8x to the 3rd. What's the derivative of the first component? Well, we've actually mostly seen that. We take negative 1/2 out front. I take 8x to the 3rd y squared minus 9, raise that to the negative 3/2 power, and then I multiply times the derivative of the inside function. This is with respect to y, so we're going to get 16x to the 3rd, y to the 1st. That one's a little bit shorter than the last one. I'm still going to clean that up. F sub y cleaned up a little bit. Negative 1/2 times 16x to the 3rd y times 8x to the 3rd y gives me a negative 64x to the 6th y to the 2nd power. Again, I'm multiplying the negative 1/2 times this piece, which is raised to the 1st power, times this piece, which is raised to the 1st power. And all of that then gets multiplied by this messy component. Plus, whoops, plus, and then 8x to the third times that same messy component raised to the negative 1/2 power. So f sub xx and f sub yy are now computed. The last thing to do is the mixed partials. It doesn't matter which one you do. I will take f sub x and I'll take a derivative with respect to y of that. So just to recopy that. So I'll go x then y. Again, there's y parts and there's y in both pieces. So just like always, we're going to have to take the derivative of the first part times the normal second part plus normal first part times the derivative of the second part. The derivative of the second part, whoops, my apologies. So plus the normal first part times the derivative of the second part. Derivative of the second part with respect to y now is going to be 24x squared y to the first. Derivative of this first component with respect to y is going to be negative 1/2 comes out front. I take that entire thing and I reduce the exponent by 1. So I get that entire thing raised to the negative 3/2 power. And then I multiply times the derivative of the inside function with respect to y. With respect to y, that inside function is 16x to the third, y to the first. So the mixed partial x f of xy, I can clean this up a little bit. I get negative 1/2 times 16x to the third y times 12x squared y squared. So I get a negative 96 x to the fifth y to the third. That's what I get when I take this x to the third times x squared and then y times y squared times this part. Can't forget that part. Plus the second one is 24x squared y times that thing raised to the negative 1/2 power. So that's the mixed partial f sub xy. And we know that that's also going to be the mixed partial f sub yx as well. A good check to see if you've gotten things right is to do the derivative of y, then the derivative of x. So in other words, if you took the derivative with respect to x of this one, you should end up getting the same thing as if you did x then y, just like I did. So if you do derivative with respect to x, then derivative with respect to y, that's the same as if you do derivative with respect to y first, and then derivative with respect to x second. So there's your mixed partial derivatives. So now you have all 4 of the second derivatives. Now, in this case, and in the previous case, these were pretty messy ones. That's just to show you that sometimes a function that starts out looking fairly nice, once you get into those first derivatives and then second derivatives, they can get fairly ugly pretty quickly. Now, what if we have a function of where we're inputting ordered triples instead of ordered pairs? Well, if we're doing ordered triples, then we can take a partial derivative with respect to x, and we can take a partial derivative with respect to y, and we can take a partial derivative with respect to z of our function. And we do it the same way as we always do. If we're doing a partial derivative with respect to x, we do the f of x plus h, and we keep y and z constant. And we take the limit as h goes to 0 of this fraction. And we do the same thing. We keep x and z constant if we want to take a partial derivative with respect to y. We keep x and y constant if we want to take a partial derivative with respect to z. So partial derivative with respect to the variable, we can take any of our three variables, and we can take partial derivatives with respect to any of those three variables. Let's do first and second partial derivatives for this function. Now, this looks like a fairly complicated function, but in reality, these are not going to be nearly as difficult first and second partial derivatives as the two functions that we've previously done. So the two immediately before this. So this is basically a polynomial function, except we're dividing by z to the sixth. And so let's take the first and second partial derivatives. All right, so the first partial derivative with respect to x, this term 2x squared, if I take a derivative, I get 4x. With respect to x, 4z to the third is constant. Also, negative 10y to the fourth times z is constant. This 19x over z to the sixth, I'll probably think of this as 19x times z to the negative sixth. And if I take the derivative of that with respect to x, that's 19 times z to the negative sixth. So my first partial derivative, f sub x, is 4x plus 19z to the negative sixth. My first partial derivative, f sub y, well, 2x squared is constant, so that becomes a 0 when I take the derivative. Negative 4z to the third is constant with respect to y, so that becomes 0 when I take a derivative. Negative 10y to the fourth z. When I take a derivative with respect to y, I get negative 40 y to the third times z. Z is just a tag along like a coefficient. And then because 19x times z to the negative 6 does not include any y values, that's a constant. So my f sub y is just that, negative 40 y to the third times z to the first. F sub z, well, 2x squared is constant with respect to z. Negative 4z to the third is going to give you a negative 12z squared when I take the derivative with respect to z. When I take the derivative of negative 10y to the fourth z with respect to z, I get negative 10y to the fourth. again, here we have it at z to the first power, so the 1 multiplies, and then the z variable gets eliminated or becomes z to the 0, which I don't have to write. And then lastly, 19 times -6 is a -114. So when I take a derivative, I get negative or minus 114 x z to the -7. Now let's look at my second derivatives. I'll start out doing f sub xx. F sub xx, well, 4x, derivative of that is 4. Derivative of 19z to the -6 is 0. Let's do f sub y. Why? Well, the derivative of this with respect to y is going to be -40 times 3, which is -120. Y squared z to the first. F sub zz, take a derivative of this with respect to z, you get -24 z to the first. Derivative of -10 y to the fourth with respect to z is 0. And if you take a derivative of this with respect to z, -7 needs to multiply times -114. That'll give you 798. That's positive 798. X z to the -8. Now let's talk about the mixed partial derivatives. Well, I could have taken a derivative with respect to x, then y. So take a derivative with respect to x. I already did that. And then derivative of this with respect to y. Notice that none of these terms have y in them. So that's going to be 0. I could have taken a derivative of y, then x. So take a derivative of y, I get f sub y. And then derivative of that with respect to x. Notice there's no x, so that's 0 as well. And once again, you see these mixed partials are equal. That's not a coincidence. But you can also do a mixed partial with x and z. So I can do f sub x then z. So I take a derivative with respect to x. I've already done that. Then a derivative of this thing with respect to z. -6 times 19 becomes -114. So I get -114 z to the -7 power. You can probably guess what's going to happen if I do z then x. Derivative of f with respect to z, take a derivative of that with respect to x. These first two terms have no x in them, so those become 0 when I take the derivative. When I take the derivative of this with respect to x, the exponent of 1 on x multiplies out front. X to the 0 becomes just a 1. So I get -114 times z to the -7. By the way, sometimes on easy ones like this, I like to write out all of the different combinations just so that I if I have both of these, if I've done both of these, that's a good check. Once I see that they're equal, that's a good check that I've done the derivatives correctly, those second mixed derivatives. All right, we've done x, y, we've done x and z. The last thing to do is y and z. If I take a derivative with respect to y and then derivative with respect to z of that, notice that derivative with respect to z, 1 comes out front. I get negative 40 y to the third. Then if I take z then y, so derivative with respect to z, and then derivative with respect to y. So I take the derivative with respect to y of this expression. Well, with respect to y, this term is a constant, so the derivative is 0. With respect to y, the 4 comes out front. I get negative 40 y to the third. And then there's no y involved here. So that becomes a 0 when I take the derivative. So notice that we had a lot of different partial derivatives here. Every time I have mixed partial derivatives, the f sub xz is going to be equal to the f of zx. F sub xy is going to be equal to f sub yx. F sub yz is going to be equal to f sub zy. That's not just this function, but that's every function. Those mixed partials are going to be equal to each other as long as we have the two variables that are the same. Obviously, xy is not going to match up with xz, but in general, but xy matches up with yx. So whichever you take the order of those. And again, like I said, I like doing them both ways sometimes, and that's a good check that I haven't messed up. If you do them both ways and you get different answers, then you know you messed up at some point along the way. But there you go. There's all of the different second derivatives. Notice there's a lot of them. The 3 first derivatives. And then how many second derivatives? 9 different second derivatives. 3 first derivatives, 9 second derivatives. Let's do one more example of the first and second partial derivatives for a function of 3 variables. Here my function is going to be 4x to the third y times the natural log of z to the fourth. We're going to find the first partial derivatives and the second partial derivatives for that function. All right, so let's just get at it. First derivative with respect to x. Well, the y natural log z to the fourth, that just acts as a coefficient just like 4. So first derivative with respect to x is going to be 12x squared y times the natural log of z to the fourth. First derivative with respect to y is going to be, well, again, this is y to the first. So 4x to the third, natural log z to the fourth, those just act like constants. in this case, like coefficients, and then derivative of y is just 1. So we get 4x to the third times natural log of z to the fourth. Now, derivative with respect to z, we get 4x to the third y as the coefficient. Derivative of natural log of z to the fourth. That would be 1 over z to the fourth times the derivative of the inside function, which is 4z to the third power. I'm going to clean that up just a little bit. 4 times 4 gives me 16. I have x to the third. I have a y. And then if I have z to the third divided by z to the fourth, that's like a z to the -1 power. You could also write that as 1 over z, or this whole thing over z. But I think if I want to take more derivatives, it's going to be easiest to see it this way. All right, let's do f sub xx. Okay, so I take first derivative with respect to x, take another derivative with respect to x. I'm going to get 24x to the first times y times natural log of z to the fourth. So 24x to the first times y times natural log times z to the fourth. If I take f sub yy, so second derivative with respect to y, well, there's no y involved here anymore. So that's just a constant number. And I get second derivative with respect to y is 0. Let's do zz. And again, I'm going to use this version. So I take in the first derivative with respect to z, second derivative with respect to z, the -1 is going to come out front. I'll get -16 x to the third y times z to the -2 power. All right, now let's do the mixed. Let's go f sub xy first. So I take a derivative with respect to x, then take a derivative of that thing with respect to y. That's going to give me 12x squared times natural log of z to the fourth. What if I take the y, then the x? So I take a derivative of y first. I've already done that. Then take a derivative of this with respect to x. Well, 3 comes out front. 3 times 4 is 12. I'm going to get 12x squared times the natural log of z to the fourth. Again, mixed partials match up. All right, let's do another mixed partial. F sub xz. So we do x first, then derivative of this with respect to z. we're going to end up with 12x squared y times the derivative of the natural log of z to the fourth. That is 1 over z to the fourth times the derivative of the z to the fourth. And when that's all said and done, you get 48x squared times y to the first times z to the negative 1. Let's do the mixed partial z then x. So basically, I take a derivative of this one with respect to x. 3 times 16 is 48. X gets reduced that exponent by 1, and then y z to the negative 1. Again, notice that it's the same thing. Last mixed partial derivative pairs, let's do y then z. We've already taken a derivative with respect to y. Now let's take the derivative of this with respect to z. That's going to be 4x to the third as my coefficient. And the derivative of natural log is always 1 over natural log times the derivative of the inside function. So 1 over z, 1 over the thing inside of the natural log times the derivative of the inside function. So notice what that is. That's going to give me a 16x squared times z to the negative 1. It's not doing that. And let's do the same thing. Let's do f sub z then y. We know we should get the same thing, but I always like doing this because of trial and error. So I'm going to take a derivative of this with respect to y. That's going to be 16 x to the third z to the negative 1. Now you'll notice that I didn't get the same thing here. On one of these, I got x squared, and on one of these, I got x to the third. So I know something went wrong. That's why I like to do both of them, just so that I don't make a silly mistake like I did here. Now, I did this a little bit purposefully, but technically, when you do f sub y then z, notice I had mistyped. I put 4x squared instead of 4x to the third. I was supposed to have 4x to the third in this one. And so I should get 16x to the third times z to the negative 1 on both of those. Again, that was a little bit on purpose, that I was trying to make a mistake and show you that by doing it one way, then doing it the other, you can clearly see when they don't match up, and that is a big red flag when those mixed partial derivatives don't match up with each other. So in every other case, all my mixed partial derivatives match up. Now in the last case, the YZ and the ZY case, now they do match up. So that is how we can take first derivatives and second derivatives of functions with ordered triples as the inputs. Obviously, some of these functions can get really, really ugly, just like we've seen before, like in our square root example, the couple of examples ago, and in our tangent example, a couple of examples ago, those became really ugly, but we could still do them if we were given enough time and we were careful enough. So I wanted to just make that clear on the second partial derivatives where we have mixed derivatives that when you take the x sub y and y sub x, excuse me, f sub xy, f sub yx, those are the same. F sub xz and f sub zx are the same, and f sub yz and f sub zy are the same. Those are always going to be the same as long as they exist. So as long as we can actually calculate them, each pair should be the same. Okay, now obviously this pair is going to be different from this one, is going to be different from this one, but each of those pairs are the same. So that's how we do partial derivatives, both in 2 variable input functions and 3 variable input functions. So that's the end of this section. We'll use more derivatives and more types of derivatives in the next few videos.